Well, I think we can start. Welcome back, folks. And congratulations on making it to midterm week. We're at the halfway mark, about to cross it. As far as midterms go in this class, it's really nothing special, just a chance to say how you're doing right in the middle. But honestly, you get that chance every single week, pretty much. Every time something's graded, you can always go here. First element under the grading system is your course grade, and that's just going to convert to your midterm grade at the end of the grading of this weekend here. But it's a good place to keep on coming back to check, even if it's not midterms, since you'd always want to watch that target, see how things change, see how you can improve your score, that kind of stuff. But it's exciting. We're getting through the halfway mark. And as far as our work today goes, we're only really just starting chapter 17. We spoke some words about it last class on Thursday, just so that we didn't end, say, too early. The links down below here is purely optional reading. I think these take us to Wikipedia pages on these two figures, Ronald Fisher and William Seeley Gossett, two big figures in statistics. And then looking forward into the future, midterm week is pivotal for our class because whatever we finish on this week right here is going to be the last section that emerges on exam 2. So after doing the grading, the midterm grading, I'm going to this weekend also convert over to saying what the exact coverage is on exam 2 and publish the review documents below as well. So pretty much just repeating the exact same cycle we did for the first exam. Well, that's where we're at, folks, and that's where we're going so far. Any questions or comments at the moment before we get started today? Okay, let's jump in. So chapter 17 is like a big puzzle piece for us because we've been constantly mentioning all the way back in chapter 14, the methods have problems. You can't just assume you know sigma. And historically, they didn't. They actually used the sample standard deviation S in place of sigma, ran the chapter 14 methods as if the statistic S itself was the parameter sigma. And they didn't get into too many trouble until the sample sizes started getting a little bit low. It highlighted the logical error. And chapter 17 plugs that hole finally. Here's how it goes. Very first thing we do in chapter 17 is we make a big callback to the central limit theorem. It's also a good reminder that just because we're in chapter 17 does not mean central limit theorem isn't there any longer. Everything that we've talked about and described through this theorem still is working in the background. So that's important to say right away. Example 1 starts out how any kind of study would start off. Gather a simple random sample, and it's the sample size from a population with mean mu and standard deviation sigma. And this time we're going to be honest about mu and sigma. If we don't know one, we probably don't know the either one. And it's weird to know both at the same time. You wouldn't do inferential statistics in the first place. So the other thing that's new here is we're going to assume both parameters, mu and sigma, are unknowns. So that's the honesty in chapter 7, stark contrast to how we started off chapter 15. So we'll use the central limit theorem with the knowledge that this approximation gets better and better. We really approach normality as the sample size grows larger and larger. We use the test statistic here in order to determine what the p-value would be for a hypothesis test. And even if we weren't using a test statistic, the normal distribution tells us what the critical values are, z star, if we're doing a hypothesis test. Now, here's the trouble right here. You can't calculate z, like ever. The moment you say and admit sigma is an unknown, there's an unknown here. Z is also then totally unknown. But we can provide an estimate for the test statistic z that's still on the table for us. So this is what we're going to do next. Provide that estimate. Well, let's say here, just to clarify what's going on in the notes, we won't be calling it the test statistic z any longer when we make this estimate. The estimate of z is called t. T is the estimate of the unknown now, z, as a test statistic. Okay, so it says Determine what t is, thereby approximating z. The approximation of z is going to be relative to sigma itself, since we don't know that value. So really the first thing we do is this. First, we approximate sigma is approximately equal to something. And sometimes this is kind of tricky. Anyone know what should go here? What symbol would you put in this location that approximates the parameter sigma itself? And it's a pretty tricky question. So if you're not too sure, that's okay. I think it's kind of normal in this point of the course in statistics. But as a reminder of what would be a good approximation, think back, way back, all the way into chapter 1. And the thing we want to call back in chapter 1 is, anytime we're doing any sort of statistical study, there is the parameters. These are the unknowns. Often we call mu the unknown parameter because it's the parameter that we would approximate through a confidence interval or test with a hypothesis test. But sigma, we are now admitting, is also the unknown parameter. However, we can provide estimates. We approximate mu with x bar and call it a point estimate. And we've harped on this a lot, saying that our approximation is worthless unless we can quantify the error of making it. And now we're doing another approximation. We're going to throw in the sample standard deviation S in place of the population standard deviation S, but we're also making another change. We're not going to quantify the error in making that estimate because then it's like an infinite regress on methods. How would we quantify the error there? Another confidence interval, and that confidence interval is going to have assumptions and conditions, possibly other parameters rolled into it. It's as if we're never going to get anywhere. But that's why the work by these fellows, primarily William Seeley Gossett, is so brilliant. When we go to make this estimate right here, the reason we don't have to specify the error in making that estimate is because we're also changing the probability distribution. We're going from the normal distribution to something that's more spread out, thereby encapsulating the error in making that estimate without even quantifying it in the first place. That was the work of William Seeley Gossett in determining the student t distribution. And it's why we call it a t-test statistic as opposed to the z-test statistic up here. So we first make that approximation, then write this following interesting function, SE. SE is going to stand for the standard error. We think of it as a function using function notation, much like f of x equals x plus 1, and we call it the standard error of something. Any statistic can go inside here. Well, not quite any statistic, but the statistics that we'll put inside there are things like the sample mean x bar, or later on, a population proportion p hat. Or even later on, we might look into the difference of population means, x bar 1 minus x bar 2, or p hat 1 minus p hat 2, and so on. This is a pretty overloaded expression. You can put loads of things inside here. And if we're putting in SEX bar, it's read as the standard error. Hang on, I have a trouble with this document. It says it's not responding. Let's give it a moment. Something I did just really offended it. I think it was using that pencil tool. Oh, wow, it really got pissed off. It shut itself down. See if I can open that up again. That doesn't happen a lot, but it happened today. Sorry about that, folks. Let me just quickly jot down what we were saying. First, estimate sigma as being approximately equal to S. And then we also said here to provide an estimate for the test statistic Z. T is the estimate. We had some highlighting. Sorry about this. This is always a little bit frustrating when Microsoft Word crashes. That doesn't happen a lot. Okay, and I think we had this highlighting going here. We took a look into that sigma, mentioned this is the whole reason why we can't calculate z. We're forced to estimate it. So we estimate the unknown with the sample standard deviation s. Here's where it crashed. Then compute SE of the sample mean x bar itself. I think we wrote it in a comment, and this is where it crashed. This stands for the standard error. Okay, Microsoft Word took that pretty well this time, no crashing. So if that's the standard error, we'll say that it's equal to, in place of this whole thing in the denominator, that's just the standard deviation of x bar. When we say the standard error, we mean the standard way to approximate this unknown, that whole denominator, which came from that second position in the normal distribution here, the standard deviation. We just write in S, divide by the square root of the sample size, and the whole purpose of this is that this approximates sigma over root n. So now that we have that, we can finally synthesize all of this, come up with a new test statistic z. Well, not z, like we mentioned, we're going to rename it to t as a way to understand or communicate. The underlying distribution has changed to a new one, no longer the normal distribution. T is now equal to x bar minus the value mu naught from the null hypothesis, the hypothesized mean. And we could put s over root n down below, but it's not a bad idea to put SC x bar down below, because if we change to, say, categorical data, this goes back to a z-test statistic. We have something else down below right here, and we're just kind of matching up what all of our standard errors are really going to look like once we collect a whole lot of them. The only change is whatever statistic you put in informs the formula on the right here. Well, we did it, folks. We now have a new test statistic. This doesn't describe everything that's going on. We're changing from the normal distribution to something else called a t-distribution, so we need to describe that next. But any questions at the moment with what we did here? Okay, continuing on through the notes. The definition down here is just another way to say what we just said, but make it seem a little bit more official. So standard error of x bar is written out this way with s over root n. We have the approximation. This is the whole reason why it's called a standard error. It's not because we made a standard mistake. It's just the way to say we've approximated here in the most standard, really the best way possible. Then finally, after all that, here's the new distribution. It's a good one to pause on to really appreciate the complexity in doing a probability computation. The normal distribution is hard enough to work with, but look what's going on here with the t-distribution. This is why Gosset's work was so fundamental and really hard to uncover. When we put the standard error in the denominator, we have a new probability distribution, which we refer to as now the t-distribution with n-1 degrees of freedom. That part right here, degrees of freedom, is represented as df as a shorthand, and it's got a really great formula. Just sample size reduced by 1 gives us the correct degrees of freedom. And if we have a random variable that follows a t-distribution with n-1 degrees of freedom, this is analogous to saying z is a normally distributed variable that follows the standard normal distribution, n0, 1. But if we change from z, we'll call it t, and instead of saying it's distributed as n0, 1, we just say distributed with a t tilde, t is saying the t distribution, and n-1 is referring to its degrees of freedom. So t n-1 is just like saying n0, 1. It's specifying a probability model and something about its shape. This one took 2 parameters, the value for mu, the value for sigma. This one just takes your sample size reduced by 1, the degrees of freedom, and it describes the total shape. So That's how we indicate a t-distribution. And here's the worst part now. Here's how you actually mathematically define the t-distribution. Horrible kind of computation here. And just look at this one part. That's the gamma function. It's a continuous analog of the factorial function. And one gamma function computation is an improper integral already. This is a wildly complicated thing to even compute. Yet, way, way back in the day, look at those dates, they did this by hand and got highly accurate values. They generated a whole table of values. Humongous amount of work there. But now, with the landscape of all this technology, any calculator, whether it's a TI-84, Desmos, or RStudio more likely, it can do these computations really, really efficiently. So even though there's huge complexity, there's multiple improper integrals, and then you have to integrate that whole thing to get a value out for probability, Desmos can do it with no problem. We looked at this graph here but when we were comparing the normal distribution to the t-distribution, and the idea is, if you have a sample size 2, there's 1 degree of freedom right here, and this is like the smallest sample size possible for a statistical study, highly, highly shunned. This is only barely above anecdotal data, and we're punished severely. This is the t-distribution. The tails are very heavy, meaning the area is way spread out. And that means your value or test statistic has to be huge to reject a null hypothesis. It also means if you're doing a confidence interval analysis, your confidence intervals are very, very wide. And you know they should be, because don't forget, that's a massively wild estimate right there, for which the error is not specified. The way the error gets specified is through the t-distribution itself. Widening out the tails is encapsulating the error and making that estimate. But we also know from statistics that estimate improves. The larger and larger the sample size gets, S is an unbiased estimator of the parameter sigma. We just get more and more accuracy with a higher and higher sample size. There's always extra uncertainty, but as the sample size increases, here's what it looks like graphically. The t-distribution itself starts to converge in probability as the sample sizes gets larger and larger to the real normal distribution. This is not an illusion. I can't send n to infinity, but if I could, these curves would match up perfectly. Notice it's also curious that at sample size 30, they are pretty close. And that's the cutoff where a different author in chapter 13 says central limit theorem starts to become effective for most distributions. And that's where the t-distribution gets really close to the normal distribution. There's always a gap though, so keep that in mind. If we are making this estimate right here, we should only use the t-distribution to be as honest as possible, and that's captured here with these curves we see. No matter what sample size, always a big difference. Let's leave it around sample size 5. This is where William Seeley Gossett discovered there's a big difference between these two curves, and the blue one is the wrong curve. That's the whole punchline to his work. Let's throw that on there. So all this information, it's really just for the sake of completeness. To really understand the t-distribution, you have to know the function for the blue curve. There it is. But this is another nicer way to see it. Just see it graphically as opposed to analytically. This isn't too informative for me. It's just here for completion. Well, next thing we're going to do is describe the full set of methods, describe how condition checking works, and then rinse through some of these problems. First problem we're going to do is going to take advantage of RStudio really very heavily. Because we have raw data, we'll just import it and use t.test to give us the output that we want. And then the second question that we're going to handle is more like an exam question. On this one, I don't have the raw data, but we can still analyze this, still give a confidence interval. Purpose of example 4 is just to show how exam question could go, where we can't actually use RStudio. But first and foremost, we have to know, when does this new set of methods work? So here are the conditions that we would check. We can't check everything because some of these conditions we can't even verify. And some of these conditions are just automatic and obvious. So let's take some time here to describe each one of these. For condition one, we're not expecting too much here. Really, you just read the problem, the abstract they give us, which is essentially what we're looking at, and see if there's any information that indicates it was random, hopefully simple random sample. But for this, we'll just briefly discuss. I'm not expecting a whole lot. Just say what you can see in the problem. And a lot of times you might just say no information whatsoever or whether the sample was random or not. That's happened to us already a couple times, I believe. Now, condition two, this is just the default way of doing statistics in this new landscape. We automatically just assume the parameters are unknown, and that's why we're doing inferential statistics. That means on this part two, you don't have to say anything. This is here just for the sake of completeness to say what are those conditions. So nothing has to be mentioned. For all the problems that's going to be relative to a one sample quantitative data, that's the foregone conclusion. It's not going to hurt you if you mention it again, but I'm only giving problems with this condition automatically satisfied. Now, robustness is the big one. This is where we have to say a lot and do a lot. So let's take some time saying that. Here, give an in-depth analysis. So an in-depth analysis is going to require a couple parts. We require graphics. Oftentimes a histogram would suffice. If you feel, however, like there could be an outlier in the problem, an influential outlier, box plot might be a good idea as well, because that's going to run it through the 1.5 IQR rule of thumb and give you some graphics that show just how influential that outlier is. So occasionally we look into the box plot. But if everything looks pretty nice on the histogram, we may skip the box plot entirely. We might say our data looks reasonably symmetric. We might say our data looks at least roughly symmetric if it's a little bit on the rough edges. But this is not the full analysis. Keep in mind, let me fix that. Keep in mind that the central limit theorem is still working in the background here. And we need to combine our graphical output with a sample size all at the same time. Mention the sample size as well, which seems logical, right? Because on the robustness down below here, these are the different categories, and it's all relative to the sample size itself. So the sample size has a big influence. Even if our data is tremendously skewed, maybe it even has outliers. If our sample size was, say, 500 observations, that's totally okay. We can do this analysis. That's what robustness means. The conditions don't have to be met perfectly. Deviations are allowed, and the output we get is still highly accurate. So our output is robust against deviations from normality, is what robustness is trying to say. But only up to a point. You have to discuss the sample size and say how it relates to the problem. If you have a sample size less than 15, it's kind of like Gosset's work, low samples. And our data, the way it appears, is very influenced by these low sample sizes. It says use the t procedures if the data appear close to normal. But if the data are skewed, with their outliers present, we can't use this procedure. We need a non-parametric method in this case, which is not great. Non-parametric methods give wider confidence intervals. They're looking at the population median, not even the population mean anymore. And if it's a hypothesis test, they're less powerful as well. It's a method of last resort, basically. So it's at least 50, so above 50. Then it says T procedures can be used except in presence of outliers or strong skewness. But when sample sizes get really large, say large samples here, our author says the T procedures can be used even for clearly skewed distributions when the sample size is large. Roughly greater than or equal to 40 is our author's rule of thumb for that. Different authors put 30 here. I think that's a wise choice. He's wanting us to be conservative with our methods and really don't go too wild on the robust size. This is our author's way of saying a large sample. So even if the data looks bad, but if your sample size is larger than 40, you would mention that and say conditions are met. But the data looks really, really bad. If the outliers are just extreme, and your sample size is at 40, it may not meet those conditions as well. Keep in mind, that's what our author was saying in the central limit theorem problem. Let's actually call that up just as a quick guide to these thoughts. When distributions look terrible, you need to make another kind of judgment call. And here's my version of terrible. Hang on, I'm in chapter 13, there we go. That just didn't feel right. That was chapter 1. So this is the one distribution where violently skewed came up, and I think it's appropriate. It has a main peak here, another peak that forms way out here, causing the skew to just be out of control. And this is the view of the central limit theorem. Big failure at sample size 16. Dubiously how effective at sample size 32. At sample size 64, it looks a little bit better. And that's essentially what our author is saying. At a large sample greater than or equal to 40, this is when we expect the distribution to work, even if the distribution is clearly skewed. And we see that not quite here, but definitely on this one at greater than 40, things are looking a little bit more cleaned up. That's the central limit theorem just working a little bit better for us. But again, these are judgment calls at this point. If your data looks even worse than this situation, even if your sample size is at 64, you might have to make the judgment call, conditions are not met, even in that kind of situation. Really, there's a lot to say about robustness, and the best way to learn it is just run through a whole lot of problems. We'll be doing several problems here on these notes. We'll have a chance to discuss robustness again anytime a complete analysis comes up in a homework problem. And if you feel like you're not too sure if the data is really borderline, don't hesitate to email. I'm always happy to discuss anything relative to condition checking. It's usually an open conversation. A lot of people put input onto this, not usually one person making a yes or no on something like that. Well, that's condition checking. It's essentially what we did before, but this is the new thing that we're going to carefully discuss each time we have to check conditions. Any questions at all, folks, so far? Okay, lots to say about that, but now here's the good news. Everything we did in chapter 4 carries over quite directly. This confidence interval formula probably looks very similar to you. In the last chapter, it was X bar plus or minus a Z star. In place of SE, we just went sigma over root of n. So this is just the same formula duplicated with the standard error expressed in this way over here, if you prefer that formula. So that's kind of nice. The confidence interval formula doesn't change much. And this sentence didn't change much either, except that we said we have a T star as a critical value for the Tn minus 1 distribution, not the normal one, which has the area C between negative T star, positive T star. Really, this is the new element right here. And we can't do what we did in chapter 14 of generating out a table, because T star depends on the degrees of freedom, n minus 1. So for every new sample size, for every new confidence level, you need to recalculate T star. Not as bad as it seems though, but let's put here, that's df for degrees of freedom, the whole n minus 1. And this is the syntax that we used way back when we were in chapter 14, coming up with the table of Z star. We first specify the confidence level, that makes sense. Let's go with 0.90, since that's what's being matched here. This is a new element. We need to specify sample size each and every time. So n is going to be 10 in this problem. This is a new element, but if you use n minus 1, you might not throw it into the syntax. I like this bit in the syntax because it reminds us that degrees of freedom is not another thing new in this problem. So we'll go df gets whatever you specify the sample size reduced by 1. And here's where we'll put out T star. T star gets, well, what did we do in the last section? We went Q norm and we put in a bunch of stuff, set lower dot tail as false. There is no normal distribution. There's a T distribution. So we go Q, T. That's it. That's the function. It's kind of nice in a way. This is now relative to the T distribution, finding quantiles. We went 1 minus C divided by 2 right here. Let's look at a graphic just to convey why we did that. Reason for that was now in chapter 14. Thinking about opening it. There it goes. In chapter 14, we noticed that if we're capturing central probability C, then the tails, which are going to give you us negative T star in our problem, positive T star in this problem, involve 1 minus C divided by 2. So we just inherit that same exact syntax. I want to come out with positive T star. Let's all do this little trick as well. Lower dot tail set to false. But a negative sign here would do the same job. This is something that's easy for me to forget as well. This has one other input. Look at the yellow right above there, and notice there's degrees of freedom right after the probability that you specified. So we should put our degrees of freedom next, and then go to lower dot tail, that's way out there, set to false. Okay, that's the part that's easy to forget. We've got it. Lower dot tail equals false. Move that over. And this is the whole syntax that handles T star for any confidence and any sample size. If you like, you can reuse the syntax or just work it out from scratch. It's not a bad experience either. So let's double check. 90% confidence, sample size set to 10. That means the critical value for this problem, let me do one other thing. I always forget that you want to print out T star at the end. So let me just respecify here. And that's our critical number, 1.8331. That's actually a pretty big critical number, because if we pretended, like putting S right here causes no change, that there's no issues in the error of estimating that, we wouldn't have used 1.8331. We would have used 1.6449, narrowing the confidence interval quite a bit. But once we're honest that we made a big estimate, approximating sigma with S, this is our reward or punishment, depending on how you look at it. Think of this as a reward. Our interval is now wider because of that bigger critical number. But a wider interval just means when we go to say 90% confidence, we're accurate now. That is the real statement. Our method really does have a 90% chance of being successful. Whereas before William Seeley Gossett entered the scene, the confidence was always actually lower, remarkably lower in the right context with small sample sizes. So our whole output to this is T star. Critical numbers generically, good calls to round to 4 decimal places. So 1.8331 will do the job. We need something from the context to say less or more accuracy. And then that fulfills part A. We could do it all over again. 95% confidence, sample size 120. We'll just adjust the syntax. Come up here, 95%. Sample size at 120. That's really big. That means the T distribution itself has converged to being really close to the normal distribution, which means our value at 1.9600 should be pretty close, but we should still be higher than that figure. Let's see what happens. Run that whole thing, and it really is. It's 1.9801, double checking. That was 1.96. 200ths higher. Does 200ths matter? Maybe, depends on how big the standard error is in the problem. Depends on the context. But it's interesting to know that even at a really large sample size, there's a discernible difference in the hundredths place already for the critical number. T star is 1.9801. So those two computations is really just coming up with T star. Everything else about this problem, aside from the fact we're using the sample standard deviation, is entirely the same. So is the interpretation, the condition checking, not too different either. There's just a little bit more guidance on what we're looking at when we produce a histogram and analyze it. So we're really just redoing our chapter 14 problems now in a logically sound way. Think of chapter 14 as the introduction to inference, as our author called it. But now chapter 17, we're starting inference in earnest with the real methods. Oh, and before I wrap this section up, let's also throw this on there. I've been trying to look back into the notes on Moodle to see if I missed anything. Found a couple bits of syntax that I forgot to include. But if you yourself find anything, don't hesitate to write about it. I'll go back in there and get it uploaded right away. So that's how either one of these problems go. Now that we know how all this goes, we're going to apply this again to example 3. This one seems to be about rabbits. So it says, the scientific name for the European rabbit, which is a species from which most domestic rabbits breeds are derived, I didn't know that, is this. So there's the scientific name. We're next told a veterinary physiologist is studying the resting heart rate for that species of rabbit, which would give us a good insight for many domestic species, except that there's probably been a lot of changes in the different varieties over time, much like with dogs. But here's what the veterinary physiologist did. Full disclosure, this problem is 100% just made up. The data is fake, but it's a realistic kind of situation. Next problem is real data, though. So here's our data that we are pretending that we got as a veterinary physiologist, resting heart rates for 18 different healthy adult rabbits. So we also have a sample size here. Let's just write in to indicate it. And we don't have too much more. It just says, here's our practical question. Do the data provide significant statistical evidence that the mean resting heart rate of this breed of rabbit is below 220 beats per minute? Looking at the data, I don't know. It's kind of hard to say. Some of these rabbits were above 220. Some of them were a good bit below. Looks like a lot of them were below. This is a kind of borderline problem, not something I could really see by looking at the data. Histogram probably wouldn't help me either. We need a sound statistical method to really see if there's that statistical evidence. Well, it's a complete analysis. It provides a confidence level, so we'll inherit that as well. And for the practical question, either write in your own words or cite something out of the problem. Let's go with the route of just citing something. The practical question isn't always indicated where you find a question mark, so we really have to think about that context. But this really is it. Even if it's not a question, sometimes there's a statement of intent that the researchers want to do something. If there's a statement of intent that implies a question, you can directly copy it in here as well, or just put it in your own words, reframe it as a question. This is our second time of just directly citing it, so next time we'll make sure to write in our own. But now we're moving over to the planning phase, which is a little bit more substantial. We want to define the unknown parameter. It says choose a confidence level, but that's only if one wasn't provided. We're at 99% confidence, so we'll just inherit that value there. Try to make sure on the homework that I don't say choose a confidence level. When one is provided, I find that's kind of confusing. So the unknown parameter, that's confusing as well. There's two unknown parameters. We don't know mu, we don't know sigma. But the reason we get to say the unknown parameter, talking about one, is because we're talking about the parameter that this whole thing is estimating. It's estimating the unknown parameter mu, the population mean. So that's what we want to specify down here. We can write in mu equals you can say the population's mean, you can say the true mean, you can say the mean of all, the of all implying a population. Really, it's up to you. This is a stylistic choice. We just have to convey that it's a parameter and that the data is quantitative. You're taking a mean or average of something. I'll go along the lines of saying mu is the true. I'll go with average instead of mean. Resting. Heart rate it's a good idea to say the unit. Resting heart rate for these species is in beats per minute. If it was hummingbird, it could be a different rate since these are widely different values for different species, for example. But beats per minute looks like it was still acceptable. It's the true average heart rate, beats per minute, for all. This is my way of saying this is a parameter. We're talking about every member of a certain species. That kind of species, I'll just say for all species, or let me say all members of the species. That's a lot to say. No harm in directly conveying that down. But if you said European rabbit, that would be okay as well. Feels like a cop-out in a way. Let's do this one time. The species Oryctolagus. No idea how to pronounce the next part. I'll just write it in. And that does the job. If you said European rabbit here, that would have been okay as well. So we've got the parameter in. Confusingly, it says choose a level of confidence, but on a second take on that instructions, not a horrible thing to do because it's forcing us to put something down here, which will inform us on what we need to do on the next steps. We're going for 99% confidence. So we're just restating what we were told to do in the first place, not anything too earth-shattering. Let me change the color coding on that, though. So that satisfies the planning phase. There's no hypotheses to write in because all we're doing is confidence interval analysis. Not a bad idea to say that right here. Because this is a confidence interval, there is no H naught, no HA, since this is just a confidence interval. Interval analysis. So now let's go off to the next step. This is the most involved part of it, really. We have to check our conditions. Let's see how pathologically skewed or how bad the outliers could be in this data set. Major things we're looking to is in symmetry. Note the sample size is kind of low as well. So when we think about robustness, we have to think about the right category we're in. So next step, we don't want to type in this data. That's going to be terrible. Go into RStudio. Let's clean out this environment. And directly import from here. So first step, click on the import button. Go from text. Now my file is in this location. This is duplicated on Moodle as well. Notice there's a lot of files here. This is just more information on the T distribution itself relative to R syntax. This is all the R syntax you'd ever want to know if you're dealing with raw data and about to do the analysis that we're doing, calling t.test. And this is example 3, the data that we need to import. There it is. Beats per minute is indicated at the top. So it looks like everything is set up correctly about this. I need to scroll down on my window due to limited resolution. And here's our beats per minute data. Immediately, I just get rid of that. That's just visualizing the data. Here it is as well. And now for robustness checking, first display I want is the histogram. So let's maybe extract beats per minute first. Let's say beats per minute gets example 3, $ to select beats per minute. Then automatically we want a histogram of beats per minute. Let's now say what the units are on this. That's X label is going to be equal to resting heart rates, BPM. And there's a lot more you could say here. You could say the resting heart rates of the European rabbit in beats per minute. You could put in a scientific name. but we're also constrained on space. You can let the context above kind of carry what this statement is saying. Just give it enough so that you can fit it down below and you can fill in what the remaining context really is. So here it is, resting heart rates. I'm going to use a trick of clicking on export, copy to clipboard, and just resize as necessary. You can click on copy plot, or I'm going to take this route of Windows Shift S for just another screenshot, leaving out the thing on the top. And here's our display. From this display, we should be able to determine how badly the conditions are met or not met. Any questions so far, folks, before we go and now write out our condition checking steps? Okay, really there's just two things that we are really wanting to look into. First thing is randomization. As far as randomization goes, we're looking back into the context on how the 18 healthy rabbits were actually selected. They told us they were randomly selected. They didn't say how, but at least that gives us some indication we do have randomization of some form in this problem. We'd have to actually, if this was a real study, look into their methods to see if the randomization was done in an appropriate way to give us a representative sample. Maybe it was our actual simple random sample. But we can say here on condition 1, we know the sample data is random. So condition 1 is met. If we didn't have any indication there of randomization, we would say it's an unknown. The problem does not indicate any randomization whatsoever. This condition, well, it may or may not be met. It may be met if they really did randomization, but didn't ever say it in the abstract. Or maybe they didn't say it in the abstract because they didn't do it. The condition is not met. Doesn't mean we stop here. It just means if I have nothing about randomization, I'm going to mention it as a shortcoming down here after giving the overall conclusion to the whole problem. Now, for condition 2, this is the bigger discussion on robustness. We totally skipped the condition that mu and sigma are unknowns because, again, it's the foregone conclusion. You can say it in here, but it's okay to skip. Looking at this, the data look weird, absolutely. There's a peak over here, another peak over here, with some separation between. RStudio tries to choose the widths of these rectangles in the histogram to highlight where the data is really accumulating. It did that all automatically. So this is a pretty big feature of the problem. Bimodal data. But you know what? As a bimodal data set, how symmetric would you all say this is? Would you say skewed, or would you say roughly symmetric, or would you say fairly or highly symmetric? I would agree with that. Yeah, go ahead.
I would also agree, kind of roughly symmetric, a little bit skewed, since it's not perfect because there's a middle gap, but it's still, for the most part, it's symmetrical.
I totally agree. Yeah, it really is kind of uncomfortable, right? Usually when we think about symmetry, we go to one mean peak, visualize folding the paper on half in that way and seeing how well the histograms match up. But not if it's bimodal like this. Like you were saying, there's a gap in the middle. The average distance between the two main peaks is where we kind of visualize for symmetry. Maybe somewhere around here. And yeah, go ahead. Not at all. I think that would be a justifiable thing right here. Not in this situation. For bimodal data, we could still run the procedure. It might not be a bad thing to say, just as extra information about the distribution we're looking into. But yeah, if you said this was highly symmetric, you know, I'd see that kind of fits in. This looks like it's between somewhere on symmetric, fairly symmetric to highly symmetric looking data, depending on how you view the symmetry. If this is the line where I would fold across, slight skew to the left, very slight. but it was not something I can really see unless I try to draw something on that. So that's indication already, symmetric data. So let's say for robustness, these data are, I think if I was to give a response to this, I would say highly symmetric. But it's a judgment call, right? If you did say symmetric, or if you said fairly symmetric, or even if you said roughly symmetric, rough symmetry might tell me you're thinking about the skew here and just judging how severe it is. Those would qualify as well. I wouldn't take off points. I might just give an additional comment, maybe justifying why I personally believe it's highly symmetric. But as long as you did the analysis, the qualitative analysis of looking into the histogram and judging these kind of things, that's the main thing I'm looking for. So here, roughly to fairly symmetric would qualify. But the major thing here is we wouldn't say that these data are skewed in the sense that if it was skewed and the sample size is 18, and you're thinking about robustness, well, we don't have strong skewness whatsoever. These data that we're dealing with are really mostly just symmetric data. And so we're in a great spot. We're in this location, we're not in a large sample. So because we were mainly looking if there was any strong outliers or outliers altogether, or strong skewness is the thing I want to highlight, those didn't occur. And so that tells us robustness is met for these data. Sure, the data don't look normally distributed at all with a bimodal, but the robustness of the t distribution means we're just checking for skew and outliers in order to say conditions are not met. So here, these data are highly symmetric is probably what I would say for these data. There are no apparent outliers. So the robustness condition is met. And the robustness discussion here is a pretty big discussion. This is actually easy to forget when you really get into it. You've done all your graphics, you've done your analysis. Easy to actually forget the punchline. So don't forget the conclusion down here. Don't forget to conclude is a decent way to say it. And now we're done with condition checking. It's not too involved, but it calls back to some of the things that we were doing at the very start of the course, looking at the data and making these qualitative assessments. Now, next thing we'll do, actually compute everything. We want to compute the T star critical number. We want to compute the whole confidence interval and do it relative to 99% confidence. And right above, that's the whole process right here. But these data are raw data. Whenever you get raw data, that's kind of exciting because we can go back here. And here's how we're actually going to analyze these. We go t.test. Let's start organizing the syntax a little bit better. Purpose of the first bit here is condition checking for robustness. And down here, this is the confidence interval with C set to 0.99. Again, that's a really important reminder. Just writing this down is massive protection against making a mistake in t.test because the default confidence level in t.test is 95%. So we need to actually make a switch on that. So here's how t.test goes. Doesn't really say us too much for us right here, but we throw into it our data, beats per minute. Next, we have to control what our confidence level is. So a lot of these things you can kind of guess, just type slowly. Confidence, there it is. Confidence level comes up. It tells us the confidence level of the interval, so we're definitely on the right track. Hit that function, switch it to 0.99, and this does everything all at once. kind of a nice way to do statistics. So hit Control A, Control Enter, and here's the output. One sample t-test, that's kind of nice. It tells us what we did. It says we did a t-test. That's weird, right? But keep in mind, RStudio is really trying to give you the entire analysis. A hypothesis test is never done in isolation. You combine the hypothesis test with a confidence interval analysis as well. That's our confidence interval right here in the middle. So it goes from 200 up to 217 without the rounding there. It tells us that it's at 99% confidence, so that's a thing we double check to make sure we have the right interval. It gave us the sample mean of X, but that's not too relevant to us. It gave us a whole hypothesis test, but we're not doing a hypothesis test. So really, when you go to output this result, only output the part that's really relevant. It's this right here. You can either write it in on pen, you can hit Control C to copy, Control V to paste it in. It looks kind of rough, but I'm used to reading that output. If you're okay with that, that's an okay way to express it. Or you could just take another screenshot. But if you do take a screenshot, I encourage you not to do that screenshot, because that's not the analysis we're doing. This is the entire analysis of this problem, and the hypothesis test isn't even right. We're not doing that test as implied by the practical question. What you should do is either take a targeted screenshot, like that. That would convey to me, you know exactly which part is the confidence interval. Or if that's kind of hard to do depending on your machine, just highlight the relevant part, smack it with a big screenshot. I'm okay with this as well, because now you're directing to me that you know this is the part of the confidence interval that was expected as the output. So lots of different ways to do this, kind of like with any section of these notes. One way I would do it personally is totally different than all of those options. I'd write in my result this way. Well, first, let me just drop that down here so I don't have to worry about memorizing the numbers. For the necessary computations, I would probably write in X bar plus or minus T star times standard error of X bar. When we go to compute that, I wrote this in just as a reminder to me. That's the formula for the confidence interval. We need that when we're doing this without raw data. So this helps us memorize the method. But it implies that from 200 point, I'll round to the nearest 10th, beats per minute, this value is less than mu, which is less than 217.0 beats per minute. And what the heck, let's leave that on there as well, the output below. So this would be option one. Just write it out. Use digital ink, use ordinary ink on real paper, and just write out what you have. That's a great way to do it. I like to write this as not an interval as A to B, but as an inequality, because it reminds me that parameter mu is right in the middle, and that's just going to inform how we do the practical interpretation. So that's option one. Option two is just a screenshot. It can be a pretty large screenshot, but if it is, try to target this portion right here by highlighting something along those lines, or maybe even just doing this. If you go like this, I guess we can leave this on there. Let's call this option three. Option three is kind of sketchy. This is not something you want to put down on like a real report that you're expecting to be critically looked at, like a thesis defense, because you didn't do all of this analysis. So if you go with option three, you need to directly convey some way, somehow, that this right here is the answer. Boxing it out is a pretty traditional callback to what we do in math way of doing that sort of thing. So that'd be just fine with me as well. Well, any questions at all, folks, on either running the syntax or different ways of conveying the answer? Okay, Kind of a cool way to do analysis, right? All we did was we imported the data. Condition checking is just what we did in chapters 1 and 2. And that's the entire statistical analysis. So let's put that down here just as a reminder. Oh, geez, that wasn't the right thing. Let me try again. So here's the entire syntax for our analysis. But we're not quite done. We now have to give the so-called practical interpretation, pulling in the context. Really, there's three different big elements. We have to mention the confidence level, and we really have to say we have this level of confidence. It's not a probability any longer. 99% confidence is the success rate of this entire method, starting with identifying a population, selecting a random sample, and all the rest of the steps. We have a 99% success rate. That mu is actually in whatever the numbers provided. So we mentioned the confidence level. We write out this estimate using no special symbols. And what's the third thing? Mention any shortcomings that look like they were critical. I don't think we saw anything critical with robustness. And randomization, not super critical. We knew we had a random sample. Sure, we didn't know it was a simple random sample, but if you didn't mention that there, I would say that's okay for our problems. So let me collect the parameter, grab this, recall confidence is at 99%. And here's a practical interpretation. We'll say, we are 99% confident that, read out this sentence here. If you paraphrase it a little bit, that's understandable, but we really have to capture this, the essence of this. You have to say average, for example. You have to mention the unit beats per minute and so on. We are 99% confident that the true mean resting heart rate. I'm not going to mention the unit beats per minute. I'll mention it after we state the actual values themselves. For all members of that species of rabbit, I'm going to paraphrase that to say for all members of this species of rabbit. Okay, so we know what the actual scientific name is, but we are a little bit terse over here. And finally, we're just going to say is between those two values. Is between 200.8 beats per minute and 217.0 beats per minute. So this gave a practical interpretation of the confidence interval, but it's actually deficient. We didn't give a practical interpretation to the whole problem, however. There's still one thing missing. To find that missing thing, let's go back up to the top of the problem. Sorry for all the scrolling. Recall what the practical question was. It was, do the data provide significant statistical evidence that the mean resting heart rate of this breed of rabbit, we're talking about the parameter, all members of that species, is below 220 beats per minute? We really have to come back here and address that question. So let's take a screenshot just as a reminder. Come back down here and finalize our conclusion. Okay, so we have from 200 to 217 beats per minute is estimating mu, the parameter, or there's just a different way to say it. All those values are really below 220 beats per minute. That means we can answer this question in a yes. We do have that statistical evidence. But the question was 215 beats per minute. Now we have a problem because 215 is inside the interval itself. In that outcome, we would say, no, we don't have statistical evidence that mu, the part in blue, is actually above 215 because it can range to all the way up to 217. So it wouldn't really be below, not above 215. So if the value in question is inside your interval, the answer is an automatic no. If the value is outside the interval, and they're talking about below 220 beats per minute, and our values, upper limit and lower limit, are both below, we get to say yes to that question. So let's say it here. Well, let's not actually say yes. That seems like we're talking to ourselves. Let's just directly address that question. We have significant statistical evidence the true mean is below 220 beats per minute because 220 beats per minute is less than 217.0 beats per minute. Let me fix the unit, beats per minute, which is equal to the upper limit of the interval. So that's our conclusion to the overarching practical question that required a confidence interval analysis. And when we said the upper limit of the confidence interval, that's what we were referring to. To really be below 220 beats per minute for the parameter on average, it was all about how big did this one get. What we did, folks, we gave the full analysis, we even checked the robustness conditions, and addressed the overarching question of the whole problem. By the way, this last question here could have just been rephrased as a hypothesis test. Not that test, that's the wrong one. We're not comparing to 0, we're comparing to 220 as a two-tail test. And whatever the conclusion is for the two-tail test would directly match up with the conclusion of the confidence interval, as long as your level of significance is exactly 0.01, matching up with the 1% dual to the 99% confidence here. So a two-tail test always matches up with this analysis, but this analysis gives more. It gave that conclusion you'd have gotten from the two-tail test, and it actually provides the estimate of the parameter as well as a follow-up to that practical question. And you can imagine if all you did is the hypothesis test and you only gave this conclusion, the person who might employ you to do this statistical work might have then followed up with, well, then what is your estimate for the resting heart rate for this species of rabbit? If you never said that anywhere, then the analysis is lacking. So it's in that way that confidence intervals and hypothesis tests never exist in isolation. We have the other side effect that's a little bit rough. Only the two-tail test matches up with our confidence intervals in their conclusions. And that's one of the reasons some people feel like the two-tail test should always be thought of as the default. You need very strong reasons to change it to a left-tail test or a right-tail test. But I think we've said just about everything we can say about this one. This is our first run through on a confidence interval for a real actual statistical inference method, one that's used essentially all the time. Any questions at all, folks, on running through this? Okay, with what we'll do next is, let me move this up a little bit further first. We're just going to do it again. This is an important method, so doing one problem is just not going to cut it like we did in chapter 14. We should always do multiple problems. The purpose of example 4 is no raw data. That means t.test is off the table for us. That's kind of unfortunate, but also means that this problem can be a version of a real exam question. But as a real exam question, even here, there's certain things that you can't do. You can do the degrees of freedom. You can construct a 95% confidence interval as long as, let's say this here, on a real exam, the critical number T star is provided. We do all the computations of T-star ourselves, even if this was a homework question without raw data. We'll go to the syntax above and find it. But on an exam setting, I'm more interested in the concept of, can you put it all together once you have T-star and then interpret the output? So with that adjustment there, this is a real exam question. I mean, not really, I can't ask it again, but it could have been. And we've got 4 minutes. Don't think we have enough time to actually run through this whole entire question in 4 minutes. We'll come back to this one on Thursday. But any questions whatsoever, folks, so far with where we've ended up? Okay, well, we'll make this our stopping point for the day. If you do have questions or comments, feel free to see me. I'll be happy to help out. Otherwise, I'll see you all in Thursday's class. And if I haven't gotten you your exam back, it is down here. But you're always welcome to just directly email me. I'm happy to scan it and send it back to you. Oh, I forgot to mention also, Tuesdays are the days where I don't actually have a class after this one. So you don't have to get out of here right away. If you do have questions, you want to hang it back for a bit, I do have time for that. Thanks, you too. Take care. Yeah, Monday, Wednesday, Thursday, yeah. So that's why Tuesday's a little bit weird. Yeah,
I'm having a hard time studying up these problems for assignment 6.
yeah. So on exercise 2
Yeah,
says, you read that a statistical test at a significance level 0.05 has power 0.78 for specific alternative. What's probability type 1, type 2? Where I would go for that one is go to the chapter 15, forgetting my chapters here. Yeah, it's kind of a weird one. I think some people like that spot because sometimes people don't necessarily want to be observed all the time. And you're kind of totally out of my field of view at that point.
it's also look up there.
Oh, I did not know that. I don't know why people choose that spot then. But here's where you want to be to answer those kinds of questions. It was asking for probability of type 1 error. So you can answer that by just finding the significance level alpha in the problem.
So is that all that needs to be done is just finding alpha?
Yes, exactly.
It gives me alpha that's 0.05, so is the type 1 error just 0.05?
Yep, exactly. The moment you spot it, you've got it. And for type 2 error, well, I believe they gave you power, right?
Yeah.
Now, the good thing about that is power is 1 minus beta. But if you want beta, you just go 1 minus power now, solving this equation for beta. So if you have power, you just drop it in. Now it's an equation for which beta, type 2 error, can be solved.
Okay. Type 2 error just equals beta?
Well, it would be the value for beta, 1 minus whatever power is, but yeah, that's the symbol for it, beta itself.
Well, really this time,
Mhm.
yeah, this is this time 5.
Yeah,
And what we were talking about today made me wonder if I was on the right track or not. I'm wondering what the unknown values are. So like broken exercise 5.
gotcha.
And it does give the population
Mhm.
mean and standard deviation.
Yeah,
But like, like with the chapter we're in right now, kind of like state for all intents and purposes, you just kind of say we don't know mu for sigma.
Well, this one is actually slightly different than what we were even looking at today.
We're doing P.
If you go back up to the top, here's kind of the sketch of what's going on in this one. Or not in the top, but the start of the problem itself.
Oh, okay.
Sorry about that.
No, you're good.
Yeah, so we first have, like you said, parameter values are provided on this one. Distribution of heights of young American women is approximately normal with mean 64.5. But that data was national data. And in the national data, I'll forget how little this is, U was 64.5. But that's not actually your population in this problem. Because now it says,
That's what I was, our population is just University of California,
exactly.
Irvine.
When we
Okay.
go to a subset of that population, this isn't even the sample. This is the university. And here you write out the new parameter mu. This is gonna be the mean
Okay.
height for all females in that age range from that university, University of California at Irvine. And then from there, we got another subset, a sample, where you're getting the statistics like X bar, for example.
Okay.
But this is a funky chapter. We still need a sigma value. And I believe we're using the 2.5 on this one. Sample standard deviation 2.7 is a little bit higher, but that's S, not sigma.
Right. So when we're doing like the math for this, we use this and this as mu and sigma, even though that's not what I write in up here,
Yeah,
right?
and
Okay.
actually, this problem has more than one way to really do it. If you use sigma, you're following our methods to the letter. Right? That's automatically what we were supposed to do.
Mhm.
If you used S though, that's a little bit weird, right?
Mhm.
This is what was done historically before William Seeley Gossett in chapter 17. They literally used S. The reason it would be slightly appropriate in your problem is that it's bigger. And bigger means you're gonna make out a wider interval. This one's making it really narrow and it's using a value that may not even be accurate. So it's almost appropriate to really use the larger value, admit uncertainty, force your interval slightly wider, actually use the sample standard deviation. But if it looked like this, I would back off and say, yeah, that's gonna narrow in your interval, probably not a good call anymore.
Right.
Maybe just follow to the letter really, 2.5.
Right.
So I'm actually expecting a couple answers on this one, both pretty much equally correct. This one's slick because it's giving us a conservative estimate, wider interval. And this is what was really done in the past. But with sigma, you're following it to the letter. That's appropriate as well.
I'm just looking over the, so. Maybe I can use this to really get the finish this, or maybe just go to this one. Oh, yeah, and so what are the necessary computations and for what?
For like the conditions or for, say, the actually computing the interval itself.
Is that really all we're doing is just computing the interval?
Yeah, on this one, we didn't have any data that we could throw into a histogram, so we can't even do condition checking on this. You're pretty much just following the letter of the formulas, seeing what it's gonna output.
Yeah, I have it written in there, but like we're assuming everything's standard, there's no outliers.
Yeah,
And so is this appropriate? An appropriate way to write the answer?
yeah, that's a great way to say it.
Okay,
Absolutely.
cool. And well, yeah, that pretty much answers my question.
Awesome, glad to hear it.
That helped a lot.
Yeah.
Thank you.
This is kind of common, actually. We're gonna see in chapter 17 when we do hypothesis tests. Because in hypothesis testing, we're comparing an unknown parameter with some other different parameter that may be an estimate itself. But we're making comparisons from one population to another, oftentimes in the hypothesis testing.
And the hypothesis is testing whether this matches this, not this.
In the hypothesis test itself, it's gonna be more about, do we have statistical evidence that mu is different from that right there?
So that mu is that not,
That's
or
accurate,
not.
yeah.
Okay,
It's gonna be the 64.5. So
okay,
this is the value to be tested. And the logic here is we're basically saying, is my university essentially the same as the entire nation with
right,
respect to that parameter?
okay. Perfect. All right, then, yeah, that answers everything I had, but we still don't know mu or sigma, even though we're
Correct.
testing again. Yeah.
Lots of unknowns, yeah.
Awesome, thank you.
Yep, you betcha. Any questions over here?
Wondering if we did that one correctly, if that makes sense.
So power is 1 minus beta, it'd be 1 minus that, because power was, yeah, that looks good.
Okay,
Awesome.
and then power is the probability of correctly concluding the hypothesis, right?
Yes. That's the write out down here under example 3.
Yeah. That's still confusing, but.
It is very
Okay.
confusing, yeah. It's one of those things where you want to kind of read it out slowly,
Mm-hmm.
do it again for a specific problem, compare what this is saying, compare your write out. And then for me, it's a matter of just rereading it a couple times to
Yeah.
make sure I didn't miss anything.
Been working through assignment 6 and it's just hard.
It is, it is. We're getting over the hump though on
Yeah.
that one.
The next exam, quarter exam.
It's gonna be pretty much the same kind of concept questions. So
Okay.
once you've gone through it in the homework and see your feedback, I'm not asking anything too different.
That's fair.
Well, any last questions before I wrap it up, turn off the machine, all that?
So for the practical interpretation of the statement, power equals point. This is a exam exercise. You got it right there, don't you?
No, this is the document we're just looking
Okay.
at.
It's exercise 4 of assignment 6
Mhm.
of part A. So would it be like, we have 57% probability of correctly concluding and then bringing in the context?
Yeah, absolutely.
Okay,
And then you say when in fact, the true mean is actually less than
okay,
whatever the value was set to be.
so that's not. So that's when H naught is true, not the alternative.
Sorry, what was that again?
That's when H naught is true, not the alternative one.
So for power, it's gonna be probability of correctly concluding the alternative is true when a specific
Okay,
alternative,
so when the alternative is
Yeah.
true. Okay. That makes sense. Hopefully the rest of this goes smoothly.
I think you're in the concept questions mainly right now, and the next ones are gonna be more run through the computations next,
I think so.
which definitely goes a little bit smoother. The syntaxes and the notes will help out quite a bit with that.
Yeah, it's just exercise 4 and 5 now.
Gotcha.
Meant to make the office hours, did not.
Not always easy. Yeah, I have a wild schedule and
Yeah, I had to take the cat to the vet.
sorry to hear that. Hope the cat's okay.
She's just expensive.
Yeah.
Cause I don't live here, so I'm not in Evan Falls
Mhm.
usually, so.
I gotcha.
And then I actually have a class at the same time on Tuesdays,
Mhm.
so I'm not normally actually here.
Oh, you're in Pocatello for that class. I gotcha, yeah.
I,
Mhm.
so I don't even attend the Zooms on Tuesday.
Mhm.
I have a class at the same time in Pocatello.
I gotcha.
6 PM on Tuesdays.
Mhm.
So I watch the Zoom Wednesday mornings.
That kind
And
of
then I
makes sense,
attend
yeah.
Thursday And I attend Thursday nights through Zoom.
Well, I'm glad you made it today. That's
Mhm.
awesome. And yeah, that's not a bad way to do the class. A little bit extra work getting caught up, but if you can make it work and take opportunity to ask questions when you watch the lecture videos,
At the same time, I wouldn't recommend it,
yeah,
but your class, I guess, isn't mandatory attendance.
no, I don't have any attendance policy. That's true.
I mean, it's